So some of the terminology, frequency, wavelength, amplitude, might be familiar to some people. Who knows those terms? Maybe used them in middle school. Okay, a couple of us. So the amplitude aspect. Alright, the amplitude aspect, I don't have that labeled on your little diagram, but you guys can label that yourself. That's just the height of the wave. We will never ever actually calculate the amplitude or utilize that in our calculations here, but I just want you to know that there are some more aspects to waves than just frequency and wavelength. So in terms of what we're talking about this with respect to the electromagnetic spectrum, which is in waves, but there's a lot of energy that's represented in the EMS. So a couple of them that we've already mentioned, UV, IR. So what's UV stand for? Ultraviolet. What's IR stand for? Infrared light. There's visual, visible light, which is the color scheme that we were just talking about. What are some other waves? Those are not on this one, but sound sound does exist, but not on here. Yeah, visible, which is light. Say again. Radio waves, which I'll call that, I guess if we can call that sound. Yeah. X-rays, gamma rays, and there's one that you warm your food up with. Microwaves, right. Alright, so these are all waves that are on the electromagnetic magnetic spectrum. Some of them move very, very fast and can be quite dangerous. Some of them move very, very slow and are not so dangerous. Which ones do you think are the non-dangerous ones? Microwaves actually. Okay, microwave. Okay, so at the lab at UNC Charlotte, they have a microwave laser gun thing, and so they have it between two pieces. And what you do is to excite some whatever matter that they're using, the chemicals. They put it in the middle, and they can excite the electrons, and it does some cool things, right? But the microwave itself, if you put your hand in it, it will go right straight through your hand. It will like destroy your body. So, how do we protect ourselves from the microwaves like in our homes?
That's why it's in a box.
Okay, that's why it's in a box. But do you guys have you ever seen that screen on the front of your microwave so you can still see your food? Okay, so people say, oh, don't look at it, right? But you can look at the microwave. It's not going to eat you alive, okay? So there's a little screen on the front, and there's holes, right? The microwave, the wave itself, is just a little bit too big to fit through that hole. The actual energy, the wave, cannot fit through that hole, and that's the only thing that saves you from the microwave. So you cannot. That's why you can't microwave with the door open, because the microwave will destroy you. What if like the hole? It's the holes get turned into the. It's inside like a double-walled thing, and it's a manufacturing error. Like they cannot send that out. It's there's a lot of oversight there. Yes, you can see them. Okay.
But you'll be like,
you won't be like the Hulk, okay? Which of these makes the Hulk?
Gamma rays.
Gamma rays, okay? Those are like super, super, super small, fast, dangerous, cut right through your skin and mutate your DNA, okay? What else can mutate your DNA? What else can mutate your DNA?
UV rays.
UV rays. Okay, X-rays eventually, yes, but our UV rays are kind of up there. That's why we have like skin cancer, okay? That's mutations occur because of that, okay? And that's why we have sunscreen to stop, it's actually zinc that stops the UVs from hitting us. Okay, so that's a good background. So going back down here, we are going to talk about these two terms, frequency and wavelength, a lot, but I probably will not be writing out wavelength and frequency. I'll be writing the abbreviations for them. That's actually a V, and it has like a little tail on it, like that, V with a tail. And this is called lambda. Lambda is like a upside down Y. Okay, so that's what we'll be using. So when we're talking about frequency, we are talking about how fast things go, but we have to pay attention to units, right? Units come in a couple of varieties here. Per second, which can be written as 1 to the, second to the negative 1, or hertz. So hertz is the one that a lot of people like to use, but remember, sometimes we cancel units, so be flexible with both of those. And then wavelength is just the length, the literal length that the wave is taking up from here to here. What would be a good unit for that? Meters is the general answer, right? Okay, meter is the base unit of length. We also will see some nanometers involved as well, because we're talking about really, really, really small waves, and so nano gets us down to that scale. So the equation that we'll be using to calculate the difference, the other variables, like I could tell you red light has a wavelength of 700 nanometers. What's the frequency of that light? We will use this equation. C is equal to lambda times frequency. So C is 3.00 times 10 to the 8th meters per second. That is the speed of light. It's how fast light goes. It's pretty dang fast. That many meters per second. Okay. All right, so I'll tell the sun that. So the meters, the length here is in meters. So let's look at the units here. What did I tell you that frequency had to be in most likely? So I said most people like to use hertz, but we need to kind of recognize the other unit that's there. It's not just seconds. It's seconds to the -1, or I'm going to write that as per second. So if I write it as seconds, notice this is meters times seconds. Is that meters times seconds? No, that's meters divided by seconds. So that's why I have to write it as either seconds to the -1 or 1 over seconds, noticing that these units now match, correct? So we'll have a number here for the wavelength, and we'll have a number here for the frequency. So then we will do the math with that, but notice the units match here as they do over here. So this is an equation that you should be practicing a lot with, and you'll actually accidentally memorize it. Okay? Question? Yeah. You good? Okay. We're going to do some examples with it. So speaking of the electromagnetic spectrum, I've inverted it for you here, but these are a couple of the others that you guys didn't name, like TV. Otherwise, you guys did pretty good. Okay. The gamma rays are very small, 10 to like the -14th. That's what some of you guys wrote in your reading guide, but these are the names of those waves. And then over here, you can see meters. Okay. How long is 10 to the 4th? 10,000. Okay. AM radio, who listens to AM radio? Okay, one person. AM radio, they claim their low frequencies at 10,000 whatever, 10,000 for their meters for their frequency. Not very many people listen to that, but some people listen to FM radio. Their frequencies are falling in the like 95.1. Okay, that's 95.1 megahertz. You don't see that unit on your radio, but it's megahertz, which is 95.1. Or sorry, 9.51 times 10 to the 7th meters, or hertz. Sorry, I'm converting between meters and hertz in my head. But this right here is a wavelength about this big. That's how long your radio wave is that you're listening to in the car. There's waves that are coming out of radio towers wherever they are in the world, and that long wave that you can't see is traveling in the air and hitting your radio, your antenna on your car, and then making sound.
If you don't have an antenna,
you don't get the radio. You do have an antenna, you just can't see it. They make them smaller now. You can't see them. Okay, yeah, that's what we're talking about here, okay? Coming back to me now, okay? So that's the general idea. But as you can see, light is the things that we can see. We can hear and feel the other things. We can feel the burn of a UV. We can artificially see an X-ray because, you know, they give us those printouts and they're like, your bone is broken. We can hear the radio, but we can't see anything but this little bitty section. I don't know if you saw it. That little section right there, that's all we can see. And that makes our world go round, right? We can't, if everything was in black and white, it would be pretty boring. People who are colorblind can't see all that. Say again? I still can't hear you. Yeah. Yep. Question.
what are like the gamma rays?
They actually come from nuclear decay. So all the nuclear power plants, they have lots and lots and lots of gamma rays coming out of their machines and their chemical reactions every day. Yeah, and that's why they can only work so many days of the month, because if they get too much, if they work too much, they're exposed to too much radiation, then they get radiation poisoning and die. I don't know. Okay, we're going to calculate now. Back to me. What was the golden equation you just wrote down? Frequency, okay? So I want to know the frequency. This is a word problem again, okay? I want to know the frequency. Which variable am I looking for? V. Given the fact that violet light has it doesn't tell you this is wavelength, but how do you know that's wavelength? It's in length, right? It's in meters. Okay, so given the fact that, you know, wavelength is 400 nanometers, okay? And you also already know C. What was C again? You wrote this down.
3.00 times 10 to the
Meters per second. So this isn't necessarily dimensional analysis. This isn't a conversion. This is algebra. This is simply algebra. But you have to show your units in chemistry. We are not in math class. You've got to show these. So taking your nanometers and you're looking over here, you see meters. Do you notice they don't match? So you got to do something about that before we really proceed. So I'm going to take this equation, write down this example for yourself. I see some of you just watching. I think you should write this down for yourself. Take our equation, and let's just rearrange this equation to get what we want. What do we want here?
V.
We want the V. We want the frequency. So how do I isolate frequency? Divide by what? Wavelength. The wavelength. Okay. This is, it's called lambda, but lambda is the symbol, wavelength is what we're talking about though.
Lambda.
Lambda, like lamb,
Okay.
duh.
We're gonna call it L.
Okay, so that cancels over here. The frequency is now by itself. So I now can see that I can solve for frequency simply by taking C divided by wavelength. One second, let me finish this. I'm not that I don't answer questions, but if I can keep the flow, it makes more sense together. Okay, so our frequency is equal to C over wavelength. I have C, I have wavelength, but remember they don't match yet. So I need to get this to a more usable unit. I need to get this to meters. Remember your King Henry? Okay, so tell me how he died. And then more. Hold on. I think micro, nano, pico. What's on the side? Mega. Okay. So we're right now at nano. I'm at the nano. I want to get back to base. Okay, so that's a bigger jump. But all I need to do is think, okay, I got 400. I'm going to kind of just do this over here to the side. It's 9 zeros. Good. Nano 9. You can't forget it. Nano 10 to the 9. Nano 9.
Wait, how?
Because nano and 9, I think you can remember the alliteration there.
Oh,
Okay?
and then.
So over here, I want to convert to meters. I want to convert to meters. I'm going to put meter on top. I want to get rid of nanometers, so nanometers are going on the bottom. 1 meter has how many nanos in it? 10 to the 9th. Luke, you with me?
Oh, so this is what we've been doing.
Yeah, so it's not the entire thing that we've been doing, but this first part here just needs to get us to the units so that they match. So nanometers cancels, and then you guys calculate. Tell me what this is in meters. Question?
You lost me on the left.
Over here.
Yeah.
So all you did, let me erase this.
There's
All
a
you,
lot of,
all you're doing over here on the left was you took your basic equation of the speed of light times, or speed of light is equal to frequency times wavelength, and we rearranged the equation to solve for V. So how do we do that, guys? We divided what?
that by the
By the wavelength. Let's use our terms, okay? So dividing by the wavelength on both sides, that gave us C over wavelength is equal to this, but wavelength over here does what? Cancels out. So V now equals C over wavelength. So I just rewrote it so I have the equation written so I can work with it a little bit better. So V is equal to C over wavelength. What was the wavelength, guys?
400.
4 times 10 to the
-7.
-7th meters. Thank you. So this is our wavelength. That is what we're going to plug in down here.
Wait.
Wait 1 second. Do not ask a question just yet. Hold up. So our C value was, whatever you guys wrote down previously, 3.00 times 10 to the 8th meters/seconds. That's our speed of light. And then we're plugging in now for our denominator the wavelength we just found in meters. So that's 4 times 10 to the -7th meters. You should see now which unit is consistent from numerator to denominator. What unit? Meters. Yeah, meters will cancel. The only kind of unit, guys, the only unit left is the /seconds, which we're going to call /seconds or per second. So calculate this for me now in your calculator, and you have to put parentheses, or you won't get the right answer because your calculator does not know how you want to think about it. It doesn't know that you're thinking of this as numerator and denominator.
you lost me on the left. I'm gonna solve it again. Okay. There's one more calculator.
When you're ready.
7.5 times 10 to the 14.
14. And that's going to be per second. Great.
I think that's
Who got this? So if you think about it in terms of math, when you have exponents, what do you do when you divide them? When you have exponents, you subtract them. So 8 minus a negative 7 technically means 8 plus 7, right? But when we divided 3 over 4, well, that's 0.75. That's a 3. So in your calculator, though, you have to put parentheses around your numerator and denominator, because if not, it will not recognize that these are kind of two entities. Who got this again?
I think I gotta run on.
Okay, you guys should be writing down what I'm saying out loud too, so you guys have a sample in front of you. So if you did not get something like this, if you didn't get the 10 to the 14th, it's because you're not putting parentheses in your calculator. You've got to do that, okay? So basically, the meter canceled, the per second remains, so I just pulled it down here. I could also write that as 7.5 times 10 to the 14th hertz, or I could write that as 7.5 times 10 to the 14th seconds negative 1.
This is all one problem.
Right now, yeah. So this is your final, and that simply is just the frequency of violet light. So I told you the violet light was 400 nanometers, and then you took the equation and the relationships, and you found the frequency of it. Yeah. Yeah, that's why I need to show you guys I would try to do this always. You need more time to learn the things that are most difficult. Everybody does. So I do the more difficult things in the beginning of the unit so you have time to process, ask questions, and get the help you need. So right now you're like, what the heck is this? We're going to work through some more, okay? So let's review what we did though. We read the question. We saw the frequency was the question. We saw that the given was the 400 nanometers. The only relationship we know right now between frequency and wavelength is this relationship right here. We know that C is equal to lambda times frequency. C is the speed of light. So that's why down here I wrote that so you can remember that. So we have the same setup. Question, kind of like a given, and then not really a conversion factor, but just another piece of information regarding the problem. So noting the given relationship was C is equal to lambda times frequency, instead of just plugging all my variables in right at the beginning, I just rearranged this by dividing to isolate the V. You with me so far? Some people with me. Okay. So when you set up your V, which is your frequency, you have your C divided by lambda. So C, which we said was the speed of light, we wrote in, and the lambda, we had to find it ourselves, but we did get it eventually to meter form, and so we put the meters in the bottom. So how did we do that though? We were initially given 400 nanometers, and we knew we couldn't work meters and nanometers together because they're not the same thing. So we took our nanometers to meters by converting with our old stuff from Unit 1, metric system. So once we had that, then we could plug it into the denominator. Divide it, calculate it. Give me a thumbs up if you're okay with this example thus far. Algebra, okay? Let's do another one like this. Where's my other example? Let me just make another one, okay? So, similar style, okay? I want you guys to follow your notes that you just wrote down for processing. So, what's your favorite color, Cam? Red. Okay, so red light travels at... Are you making it up? I'm making it up. Okay. 1.2 times 10 to the 14th hertz. No, I won't write hertz. I'll write per second because I don't want you guys to mess up. So it travels at a frequency of 1.2 times 10 to the 14th hertz or per second. What is the wavelength of red light? When you write down your givens, it should suffice. If you want to write the question again. So try to start from my equation you use first. Give me a thumbs up if you made it to the identification phase. You've identified you have V. That means you know that frequency doesn't have a numerator, it's just got the per seconds, or it can be listed as hertz. People in the back who are talking, pay attention for me first, because some of you guys didn't write down the first example, that's why you're a little lost, okay? Work with me as you go. So then your question was wavelength, we're good there. C is a given, as it will always be, and that's 3.0 times 10 to the 8 meters per second. So what is the golden equation, Zane? What's the
C is equal to frequency.
So frequency times wavelength. So we have to start with this. Some of you guys will just plug in what you know, and then you'll naturally divide once you see it in there. I'm just doing that up front before I start plugging numbers in, because I can easily mistakenly put like a 2 or a 1 in the wrong place. So which one of these am I solving for?
The wavelength.
So I have to look for the hanger. I have to divide by what? The frequency on both sides. So all I'm going to do now is just do whatever what?
3.00 times 10 to the 8 over 1.2.
Whoa, what's this unit right here? So I'm doing, so basically, some of you guys are picking up what I'm putting down. Let's get this highlighter. So we're putting C over the frequency, C over V. That's what we're mathematically calculating now. So that's meters per second, as we have over here. And what's our V?
1.2.
10 to the
10 to the 14th.
14th. Not seconds.
Says seconds.
Per second. So I'm going to write that as slash second. I wrote it as a more defined fraction bar there, but I'm just writing slash second here. Grant, which unit has the ability to cancel?
Second.
Because they're both as per second, per second. So I'm canceling out per second with this per second. So what's the only unit remaining?
Meters.
Meters. Doesn't that make sense for wavelength? It should. You have to think about that sometimes, but make sure you've solved it correctly. So when you put your parentheses, and then you divide, and you put your other parentheses, and then divide, I have no idea. 1 second. What'd you guys get? Times 10 to the
Negative 6.
negative what?
Negative 6.
Was it 6? I believe you and stuff.
But you
I gotta check. I just made this up, so I gotta double check it. I was trying to make it so it worked, but I actually made it a little small. And what unit is this, guys? Meters. This is wavelength. So I made you solve it for the opposite variable. This is the answer. The nanometers thing. So what I could ask you from here, so I specifically did not ask for the nanometers because I wanted you to feel good about just taking your frequency and your wavelength collectively. But what I could ask for is, what is the wavelength in nanometers? We got it in meters, right? Sorry, right there. So we got it in meters. If I were to convert to nanometers, I would need to do the 10 to the 9 thing. Okay, we'll work with that some more. All right, let me give you a quick break for a second. Pull out, because I do want to talk about Bohr model, but I think that's going to give you a chance to take a break from me. Pull out the electron, energy, and light. Okay? You're going to take maybe 10 minutes or so and get the first little running. You're going to get the first quadrant done. Yes, you can color it if you wish. You do not have to color it, but the question up here, the first step is to color the wavelengths. So I'm going to let that sink in the back of your mind, and then we'll pick back up with Bohr. Okay? So if you need colors or crayons or color pencils, I have all these stacks right here. You're listing which section so far? First quadrant. You can move on if you wish, but some of the stuff over there is going to be relevant after I talk about it. Okay.
Is this all the Wednesday?
You can look that up. I don't know. I can't remember.
Or the Wednesday?
So focus with me out right now. Okay. I have to look it up. We don't really have that many notes today. It just takes a little bit to process it, so that's why I'm trying to let you guys process while you guys work. Alright, so you guys saw from here, you saw from here, the light we see is truly made up of many, many, many forms of said light. So the white light from like a white light bulb or from these fluorescent tubes above us, they hit a prism. The prism has the ability to separate into individual wavelengths. Each of those wavelengths correlate to a different set of colors, right? So these are all shades of red in this wavelength. These are all shades of violets in this wavelength. So a correlation between wavelength speed and photon energy, which photons, like photosynthesis, what does photo mean? Light. Okay, so that's light energy. There's a correlation here, which we're going to talk about more in a second, okay? So let's finish up some of more of our notes so that I'm not killing you guys on Monday with these. So I would like for you guys to now write down information about Bohr, and then we'll talk about why the spectroscopes are working the way they're working, okay?
Which one?
Some of this stuff with Bohr was on your notes from Wednesday, but this is just the specifics that I need you guys to write down for right now. Grant, you got me? You ready? Thanks. All right, so Bohr model, remember, it's specific to hydrogen, and that's the problem. Everybody's like, oh, Bohr, we bow down to you. You've done so much for our ability to understand the atom. And he postulated that all these energy levels existed, but as we went farther along, his theory was only actually true for one atom. It was just hydrogen, which was really not that useful. But he did make a big jump from J.J. Thomson and Rutherford to say, hey guys, you know those electrons you guys were talking about? They actually live in these things called energy levels, and that's the point that we're making now because it's still true today, at least from what we think. So he said, in terms of his model, which I have a diagram of it down here, that there are only 4 energy levels available, and those energy levels surround the nucleus. And in that surrounding feature, they actually have to get bigger and bigger and bigger and bigger because, you know, the nucleus is in the middle, so these concentric circles are larger and larger and larger and farther and farther and farther away. So this is probably the diagram you probably remember drawing in like 7th grade. Do you remember drawing diagrams like this? Yes. You put dots on them?
Yeah.
Big fat lie, okay? They lie to you in middle school so you can get through. And I tell you a little bit more, and I still can't tell you everything or your head would explode. So what I'll tell you now is that we will not draw it like this, but it's a good way to diagram out how the energy levels work. We won't continue drawing them like this for very long. So the word quantize was on your vocabulary list from the reading guide. Quantize just means it has a set amount of energy. So quanta, quantize, those all kind of relate to each other, and it's relating to a certain amount of energy. What you guys were just looking at in the spectroscopes, which if you didn't get a chance yet, you will definitely get a chance to shortly, you saw these things called spectra lines, and they're just colors. Colors/wavelengths. And we have a nice little, tool that will do that for us, and they show us how the energy gaps in the energy levels exist. So what in this bullet point right here, what it's saying is that we don't just see the spectral lines because they're there. We're seeing them because there's electrons there. And what are the electrons doing? What are they doing? I got it right here for you. They're just moving between energy levels, right? So in this diagram I've drawn for you here, the electron could be up here on the top, the 1, 2, 3, the 4th energy level, It could be out there, and it can move one direction. So I'm going to move it just down. I'm going to move it all the way down to the first one. So when it drops, that actually gives off energy, because these energy levels have different amounts of energy. Or I could draw it here in the middle, and I can make it go out to an outside energy level. Well, we maybe won't see that. That's going to be on the next slide here, okay? So as these electrons move, they change their relative amount of energy. Can I scroll down just a little bit more? Almost. Okay. What's up? I'm gonna. I have a simpler image for you on the next slide. This is a little complicated.
Yeah.
Okay. Don't worry about it right now. You're hold on. But what I want you to see is that we have these concentric rings, and the point that you should make, maybe with like a little animated drawing like this one, is that the ones on the highest energy levels are out here. EL is energy level, and the lowest energy levels are in here. And they actually are called like 1, 2, 3, 4, and we call them N. Like this is N equals 4, this down here is N equals 1. So as I go from the outside energy level, actually that's 5, that's okay. As we go from the outside energy level, N, and then like the middle energy level, N, and the closest energy level, N, what do you notice is different about all these in terms of the colors they give off?
The ones that are farther out give off less.
Hold on, the ones that are farther out give off violet light, right? And the ones that are closer in give off red. Okay, think back to what we said earlier. Who has the most energy? Red light or violet light? Violet has the most energy. Okay, and the red light has the smallest amount of energy. So what you're seeing is that the farther away from the nucleus it is, and it goes through all those energy levels, it's releasing a lot of energy. It's releasing a light form which has the most energy, which is purple or violet in this case. And the closer it is, it doesn't give off very much energy at all. It just is a quick drop. And that's not much energy, which correlates to the lowest energy of light we have, which is red. So that's what this correlation right here is supposed to show you. You're going to practice this a little bit more, okay? So looking at this, this is just a quick definition. Let me just tell you this first. We just talked about what photo meant, so photon is and it's the term we'll be using more specifically. But photon is not just light, but a bundle of light. It's like a packet of light. That's what we see, and that's that's how we see all the colors that we see every day. That's what we're seeing from the light sources above us. They're shooting little photons of energy at us. So what's happening in like this diagram here with your neon light, or even the lights above us, is the electrons are moving down energy levels, and as they move down energy levels, what are they doing? We just saw the diagram with it. They're emitting light, good. Or they're emitting photons. They're releasing energy is another way to say that. So sometimes we'll say the same thing, but we say them in different phrases. So as electrons move down energy levels, this is a key point. As they move down or as they drop from an outside energy level to an inner energy level, they release energy. If that energy is perfect inside of the spectrum of where visible light is in the electromagnetic spectrum as a whole, if that energy is right where we can see in the visible spectrum, then we could see that energy. If it's outside of that, we won't be able to see it, but we can still detect it. We can still feel heat from infrared. We can still feel burns from UV. So the energy is not specifically just visible light, but it could be. So give me a thumbs up when you're here, when you're done. And you can look through the spectroscope if you haven't had a chance already. There's some floating around. All right, so now I'm going to pause again for a second, go and do the next section here. And even farther, you can try to get through the next two sections, and then I'll do some energy calculations with you. I'm breaking up the calculations, that's what I'm doing. Go to the next section, yep. Grant, stand up for rock, Susan. I'll leave this here for you, and as you're going through, I'll put up that form or that worksheet so it's a little easier to see. Work with your partner at your table. I think it's good.
Oh, I'm not taking out like my original line. Oh, no, I don't know.
Violet and red.
So these are the spectral lines of the, I said you can. It's violet is one of the lines, blue violet, blue green, and red. Those are the 4 spectral lines in the hydrogen one. We're going to talk about this some more after you get the hang of the vocabulary. Wherever you are, finish with the question you're working on, and then we're going to pick back up here. Right now,
I think it's
Alright, so looking back here now, so what you saw was that there are spectral lines. Let me show you what that looks like actually first. These are the the spectral lines you were just looking at in the spectroscopes and on the drawings. So what this is right here is the black background. It's kind of the way you saw it through the spectroscope. And there's these bright lines. So we call it an emission line spectrum. We call it a bright line spectrum. The inverse of that, which is you see how this is inverted? That's called the absorption line spectrum. But basically, they're just showing us the electrons moving within an atom. So what you saw in the hydrogen worksheet, the hydrogen, how many spectral lines were there? 4. How many electrons does hydrogen have? 1. So 1 electron is just going boop, 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 boop. But there's only 4 energy levels that one electron can move to. What was the second example there?
Boron.
Boron. How many electrons is boron have?
6.
Boron's atomic number 6, right? So it has a lot more electrons to kind of boop around to allow them to move and then create these spectral lines. So that's the main differences between those two pictures you were drawing. So what we need to then understand about that is, how do these electrons make these lines? They're basically putting out energy, and we see that energy as color, as visible light. It falls in the visible light spectrum. But how or why? So the word is, the electrons become excited, and as they become excited, they then move their electrons. Make sure everybody's got me here, I'm paying attention. The electrons will then move from their inner energy levels and bounce out to their higher energy levels. So we call that jumping. So this electron here became excited by the addition of some sort of energy. This would be a good one to draw if you're done taking the notes now. So the atoms can become excited by either the addition of just some extra light, some photons kind of hitting it, heating it up, or electrocuting it. And we're going to do all three of those this unit. We're going to heat them up. We're going to see the electrons become excited. We're going to shock them with electricity. We're going to see them become excited. And then we're also currently, with the spectroscope, you guys just saw the light was exciting themselves.
See, what's a little thing about?
In just a second, okay? So as the atoms become excited, they're going to go to excited state. That is the terminology, when they go to an outer energy level. Well, just like you guys, think about a caffeine high or sugar high that you might get on. You can't stay at that excited state for very long. You eventually have to fall back down to neutral state. You'll fall back down to, you'll kind of crash, fall back down to what we call ground state. So ground state is the initial state, and it'll be the final state once the excitement has kind of taken place. So you start off in your ground state, you excite your electron, it gets excited, and it jumps up to the, like for example, from here to here, it's jumping to an outer energy level. It can't stay at that excited state for long, and the electron falls back down. I'll draw another picture. So it falls back down from outside to inside. What do you think occurs when it falls back down? It releases energy, and if that energy is in the visible spectrum, we can see that energy as visible light, as green, blue, yellow, purple, violet, red, whatever. So this right here, this stuff is the most kind of the more important stuff about Bohr's model, because that's how we describe them skills using Bohr's model. So that energy that's released, we can see. How do we excite the electrons? Heat, electricity, or extra light, extra excited light, so like violet light, UV light. And then they fall back down and they release the light once again, or the energy once again, which could be in the visible spectrum. That is the next part of the worksheet. Okay, keep going.
Like part 4.
Yeah, move on to the fourth quadrant in there. So I'm leaving this here, and then let me keep working on the worksheet as we go. I'll scroll full of it for you guys over there. While you're reading, you should be focusing on the content Am I just chit chatting? Because I think that if you can read it, you actually process a little bit better.
Should we draw the things next to it, like the 1, 3, and
Those are just some additional diagrams. Okay.
That's right.